Okay, welcome. Today is another meeting of New England Dynamics and Number Theory seminar. This time we are in Austria. Manuel Hauke joined us from Graz with a talk titled Pseudo-random sequences, twin primes, and twisted diophantine approximation. A lot of dynamics and number theory. Welcome.
Thank you, Dimitri. Thank you for the introduction. It's always a pleasure to speak in this seminar. I will start saying at first that the twin primes in the title might make people believe that I'm proving something with twin primes. I have to admit this at the first minute that this is sort of a clickbait thing, that I'm not proving anything on twin primes in this talk. It's more knowing something about twin primes implies something for the other things I have on my slide. So this is more or less the talk. So for everyone that wanted to come to the talk to see a proof of twin prime conjecture, I have to say, I'm sorry that that's not here. But we will still learn something about twin primes here, I hope.
But the twin prime, if we assume twin prime conjecture, will it imply something about your result?
Yes. Like if I assume a stronger form of the twin prime conjecture, you will see this later. Then we can show something. Yes.
Okay. All right. Thank you.
Yes. So I have two topics for you that are quite different at first sight. Where I will state some motivation, some results, and then in the end I will try to give like sort of a joint proof of this. So I will start with pseudo-random sequences, the first part of my title, which I call here fine-scale statistics of sequences. So what is this about? So let us take n points in the unit interval, or a sequence and truncated n after n many elements. And let's say they are somehow distributed in a unit interval. So the average spacing between 2 points is 1 over n. And we're interested in the local attraction or repulsion of these things. You can think of particles in physics, whether they have some attraction or repulsion, or you can just think in terms of mathematics here. So one thing that people are really interested in is to understand whether these points give you a gap distribution. So gap distribution means we order our points in increasing order. We start with the smallest one, order them up to the biggest one. And now we ask about the neighbor spacing distribution. So is there a gap distribution mu, usually a probability measure, such that the number of elements n, such that the neighbors xn plus 1 minus xn are of distance 1 over n, but the 1 is replaced by some interval ab. And if this converges to the measure of this, then we say we have the gap distribution mu. So what's the gap distribution that we should expect here if we have throwing just randomly points there? It turns out that there is a gap distribution that we should expect in this case. So if we take an IID sequence uniformly distributed in the unit interval with respect to the Lebesgue measure, then almost surely we get a gap distribution, and the gap distribution has this exponential density function in there. So if we have this, then we call this behavior Poissonian gaps. This Poissonian here is modeled by the Poisson process that also has these kind of statistics when normalized accordingly. So why do people care about this gap distribution? Most of it comes from theoretical physics. Of course, we can care about this for particles, as we said before, but we can also think of these numbers being the eigenvalues of some dynamical system. This is where the Perry-Tabor conjecture comes in. So this is a conjecture in quantum chaos theory in theoretical physics. And a special case of this is the Rudnick-Zanak conjecture, which is now looking way more number theoretic. So this is what I'm most interested in here. And the Rudnick-Zanak conjecture says if we have a badly approximable alpha, then n squared alpha mod 1 has these Poissonian gaps actually. So n squared alpha in this sense looks like a random sequence. For those of you that don't know what a badly approximable number is, probably all of you know this, but in case someone is here for the first time, badly approximable numbers are those that are only approximable by quadratic approximation quality. And we have some explicit examples of such numbers, such as the golden ratio, square root 2, other quadratic irrationals. And keep in mind, also a basic fact, the Lebesgue measure of the Bernoulli approximate numbers is 0, but the Hausdorff dimension is 1. So this is basic facts, probably all of you know. I just wanted to recall this here to begin with. And I want to mention that this conjecture is widely open. So far we have no clue how to solve this. We have some approaches towards this, but let's start thinking about how to prove Poissonian gaps in general. So these neighbor statistics, they are analytically very hard to catch. So it's really hard to say something about the statistics immediately. So the usual way of going here is that we look at the Poissonian correlations of arbitrary orders. So let's speak first about the second order correlation, which we call pair correlation or PPC. So for this, we just look at pairs NM. And now we look at the points xn minus xm, and if they are close to each other, we count them. And they have to be close of the average spacing, like 1 over n. Then we count them. So we fix our number r, which is just a fixed constant. And now we look at the number of pairs that are close, that are of distance at most r over n. So if this converges now to the expected number, which is 2r, so we can go to the left or to the right, we can do a simple counting argument, then we say that we have Poissonian pair correlation. We can also play this game with higher order correlations. This is just the same. So we fix our k-tuple with pairwise distinct indices. Now we ask the differences to fall into a rectangle divided by average spacing 1 over n. And we should expect that this converges to the volume. If we have this, then we have kth order Poissonian correlations. So why do we care about these Poissonian correlation statistics? They are interesting on its own because we get some information about the sequence, but it is also known that this implies to have Poissonian gaps. You can think of this morally of being some method of moments. You have the moments and you can say something about the distribution. It's not precisely the moments, but you can think that this is sort of the same thing. And indeed, if you want to show that an arbitrary sequence, or if you have an IID sample, has Poissonian gaps, this is the easiest way to show it. You show that you have all Poissonian correlations of all orders. This holds almost surely, and therefore it also implies that we have these Poissonian gaps. So this is the standard way of proving Poissonian gaps in the end. So we have this for a random sequence, but are there any other randomization processes, or are there even deterministic sequences where we notice this behavior? And there are a few. So it was recently found by Lutzko Somelidis Technau that if you take n to the theta times alpha mod 1, but the theta is small, so it's smaller than 14 over 41, then we have at least a second order correlation being Poissonian. There is a slight improvement in theta by Radziwill and Shubin later on. So the exponent theta is pushed a little bit, but it's still far from 1/2 actually, and very far from 1. So this is really a real sequence. This is not an integer sequence n to the theta here. And the alpha here is, one can say, for cosmetic reasons, because it doesn't play any role, neither in the statement nor in the theorem. The alpha here can be rational. It can even be 1. So we have an explicit example of a function that of a sequence that has Poissonian pair correlation. And if you play this game a little bit further, if you go one step more, you have log n to the a bigger than 1, then Lutzko and Technau show that we actually have all correlations and consequently also this Poissonian gap distribution. These are essentially the only explicit examples we have so far. At this point, I think one has to mention the classical result of Elkis-McMahon, who found the gap distribution of another very interesting sequence, namely the fractional parts of square root n. And they showed that this has an explicit gap distribution that is actually non-Poissonian. So they actually compute it. It looks a little bit more complicated, but they have a closed formula for this. So the first two results work with harmonic analysis, and the Elkis-McMullen uses more dynamical tools. And what I will speak about today is neither harmonic analysis nor dynamical. It's more a pure number theoretic proof. Okay, so we have these explicit examples, but as said before, we have now real numbers multiplied by alpha, and the alpha does not play any role. So this is not really a problem of the diophantine approximation. So in my opinion, it does not really catch the behavior of the n squared alpha with alpha badly approximal. We have this diophantine assumption on alpha. We have an integer sequence that we multiply it with. So what's a different way of approaching the conjecture is, well, let's assume another integer sequence an. And maybe let's say alpha doesn't have to be badly approximable. Maybe let's look at alpha in a metric sense. So there are a lot of results of this form. So we take an arbitrary integer sequence with some certain number theoretic properties. I'm not going into detail here what this should mean. Then we can show for almost every alpha, we have at least a second order statistics. Or sometimes we don't have it, depending on the number theoretic properties here. Some examples where we have this behavior is lacunary sequences, so sequences that grow exponentially. Polynomials with degree at least 2. So for n squared alpha, we have this metric behavior. We don't know what it does on badly approximal, but we have this metric behavior. At least in the case k equal to 2. We also have a more general criterion with small additive energy. But we also have examples where we don't have this metric pair correlation property. Two examples I want to mention here is the example of the Kronecker sequence. So there it's trivial that we don't have Poissonian pair correlation for any alpha. You can try to write down a proof. It's not too difficult. If you don't care too much about what I'm going to talk here, you can think of this for the rest here. You can also just try to visualize how an alpha looks like. It just has too much structure to be random, essentially. We can say with this three gaps theorem and more, and it's just too much structure to have any of these statistics. And one non-trivial example I also want to mention, because it's quite close to what I will continue talking about now, is that if we take the primes, then we don't have this metric pair correlation property. So for almost every alpha, we fail to have Poissonian pair correlation. This is a result of Elliott Walker in 2018.
But what does it mean that there is no limit, or that there is another limit?
So there is too much. So the lim sup is actually diverging in what Elliott shows.
Mm-hmm.
So there is no limit in that sense. If there was a limit, then the normalization is the wrong one.
Mm-hmm. Okay.
You will see later an idea of why this fails. Essentially, our Bohr sets are just too big. So that's the idea here. Okay, so these statements are just on a metric nature. So for the badly approximal, we can't say anything, because badly approximal, as I said before, have Lebesgue measure 0. But there is a conjecture of Larcher and Stockinger that claimed if we do not have this metric correlation property, then there does not exist a single alpha where this A and alpha sequence has the Poissonian pair correlation. So they claim, okay, let's take the primes. We know that there is no metric pair correlation property, so prime rotation does not have the pair correlation property at all. And also something I want to stress here, that all statements here are metric. So there is not a single alpha that is really constructed where we have an information here. And if we go away from this pair correlation, so from this k equal to 2 case, even metrically, there are just very, very few results. So if we have this lacunary sequence, we can do this, but we can't do it for polynomial sequences, say. So what what I did in my preprint earlier this year is that I constructed an explicit example of such a sequence, where we take a badly approximable alpha as our rotation parameter. And by this, we also disprove the conjecture of Lacher-Stockinger. And the integer sequence that I'm taking is sort of a generalization of the prime rotation. So I'm not taking the primes. The primes are too hard because we don't know the twin prime conjecture, as we will see later on. But we take a generalization of the prime rotation. So what I mean by generalization is motivated by the rough numbers. So as said before, twin prime conjecture is open. And why is it open? It's just detecting primes is a tough thing. So you can think of Goldbach conjecture or twin prime conjecture. It's just very, very hard to detect primes. But it's easier if we replace the condition of being prime with the condition that all prime factors of my number are actually big. So this is the definition of rough numbers. So we call a number T rough if every prime that divides n has to be bigger than T. So why is this interesting? Why is this close to being prime? Let's think a little bit about this. So if we take it formally, we give ourselves a roughness function f of x as x to the r of x. R of x is our roughness exponent here. And we define a set of rough numbers in the form that the number has to be f of n rough. And let's look now at the cases where r of x is equal to 1/2. I claim that this is just the prime numbers. You can, again, write down a 2-line proof as an exercise. You can see if a number has a divisor, and if the divisor has to be bigger than the square root of the number, then there are no proper divisors. So this means that this is just another characterization of the prime numbers. And by a similar strategy, you can see that if we choose r of x as 1/3, then we have at most 2 prime factors, because one of the factors would have to be smaller than n to the 1/3, which does not work with this assumption. So we have at most 2 prime factors. And since people cared a lot about the twin prime conjecture, they tried to look at these kind of things, and they realized here we can prove the twin prime conjecture is true on this set. So there are infinitely many numbers nm that have at most 2 prime factors, such that n minus m is equal to 2. And this is proven by using this roughness function here. And in general, the philosophy is the smaller r of x, the easier it is to detect rough numbers. You get more numbers, and it's easier to play with Sift theory, which is what usually is done in the twin prime conjecture. And this philosophy is also used in my result now. So we take our roughness function f of x as x to the r of x, and now the r of x has to go to 0. We don't need a speed here, it's just that r of x has to go to 0. So if we go back here and think of r of x being 1/3, we had at most 2 prime factors. Now we need unboundedly many prime factors, but the speed of it, this is arbitrary. We can choose this. We also have a lower bound of r of x, which is more of a technical nature. Essentially, this just says we have a roughness condition. So if we don't have a roughness condition, then this would mean we just have all integers in the end. So we know for all integers, we have too much structure. So this condition just gives us some growth rate, some sieving of the roughness condition. But let's not speak about this one too much here. So if I now take all these rough numbers and multiply this with my badly approximable number, then I actually get all Poissonian correlations of all orders and consequently also Poissonian gaps. On the other hand, if my number is a little bit better approximable, so in the sense of we get approximations essentially 1/n squared log n, then we no longer have Poissonian pair correlations. And you can think of log f of n to be essentially log n. So if we apply Khinchin's theorem, we know that this is a condition that holds for almost every alpha. So in particular, we fail to have Poissonian pair correlations for almost every alpha. So as I said before, this is the first explicit sequence with any correlation property, actually, and we get all of them immediately. And it is a disproof of the Laha-Stockinger conjecture, because metrically, this fails to have Poissonian pair correlation here, but we have it for badly approximable alpha. So there exists one alpha where it holds. So I will not talk about the proof of this one now, and we'll go to my second topic, but maybe I'll stop here if someone wants to ask a question already now. Okay, then let's continue. So let's go to a second topic, which is now like a restart. So if I lost you in the first part, that's now more classical diophantine approximation. So I invite you to join in again in what we are doing here. So let's talk about twisted diophantine approximation. So what is the classical setting here? We take our error function psi, say a nice monotonic function psi, and we fix our irrational parameter alpha now. And now we look at the set of inhomogeneous parameters gamma, such that n alpha minus gamma is smaller than psi of n infinitely often. So n alpha approximates gamma with quality psi of n infinitely often. So I also have a dynamic language of this set here, which sort of is, in my opinion, more natural than the classical metric diophantine approximation, because we have a fixed irrational parameter here. So we fix our dynamical system alpha, which is just the irrational rotation. And now we just look at the starting points, gamma. So we fix the starting point, and then we look at the orbits. And we ask, how often does my orbit come into a shrinking neighborhood of 0? And if it comes infinitely often, then this is equivalent to the starting point being in the set as psi of alpha. So this is the classical twisted setup. So of course, we want to understand, is there a Khinchin or a Bouret-Cantelli behavior for this set? So can we say, okay, we take a nice function psi, we fix the alpha, is the Lebesgue measure either 1 or 0, just depending on whether the sum of the measures, which is just the sum of the psi of n's, diverges or converges? And as you might expect or might not expect, the answer depends on the diophantine properties of alpha. So let's see what is actually the result here. So let's speak shortly about convergence case. This is trivial by first Bouret-Cantelli lemma. As always with these questions, this is just sum of measures is convergent, so the Lebesgue measure has to be 0. So let's speak just about a divergence case from now on. So we take the set curly M as the set of all monotonic functions psi, such that the sum of the measures diverges. And now let's look at the set K of psi, which is the set of all alpha, such that the Lebesgue measure is equal to 1. So this is the set of all alpha, such that psi is nice, so that such that psi has this behavior that we should expect here, the Bouret-Cantelli behavior. So what Kurzweil's result now states is the following. First of all, if we fix one of the psi's, then almost every alpha has this condition that the Khinchin type behavior holds. But note that this set K of psi depends on psi. And there are uncountably many functions psi in the set M. So we can't say anything about does my alpha now satisfy this condition for every psi? And indeed, there is a really, really beautiful characterization of the badly approximable numbers, saying that a number is badly approximable if and only if it satisfies this condition for arbitrary psi. So if my number is badly approximable, I have this Khinchin type behavior. If my number is not badly approximable, there exists a psi such that my Khinchin type behavior fails. So in particular, we can see from the second point that this set, the intersection here, has Lebesgue measure 0, but Hausdorff dimension 1, because we know what holds for the badly approximable case. So this is a very classical result of Kurzweil. And I still have it here on that slide, just for you to see what the result actually means. And now we're going to generalize this. So instead of having all integers that we multiply with alpha, so instead of looking at the Kronecker sequence, we now just look at the subsequence again. So let's take our favorite subsequence an, and now we ask, how often does the orbit of a and alpha approach gamma with quality psi of n? And again, in dynamic language, this is just the orbit stopped at certain subtimes of the sequence that this approaches gamma infinitely often. So let's denote this by SA and SKA. And now we can ask, are these results of Kurzweil's 1, 2, and 3 still true? Do we have this for arbitrary integer sequence, or does it depend on the integer sequence that we are choosing here? So let's start with the first bullet point. This is quite easy. There is Caster's doubly metric Khinchin theorem. And with a simple application of Fubini's theorem, it's another exercise, we can show that the first point holds for arbitrary integer sequences. So the first one is true regardless of which integer sequence we're taking. And for the second and third point, it's more difficult. So this is...
Can you remind me what's the first one?
The first one is...
that the Lebesgue measure is full.
Yeah, exactly. Okay. So it's sort of a two-dimensional statement. If you apply Fubini, you can come from a two-dimensional statement to the one-dimensional on the fibers. So this is how you can prove this. Exactly. So what my theorem now says is we take an integer sequence an that is multiplicatively defined. I'm not stating here the technical assumptions. I will give you some examples that you can see how this theorem can be applied. And then if we look at 2, in the classical case, this set of the intersection here was equal to the badly approximable numbers, and we can still recover a little bit of this. So it will contain the badly approximable numbers, and it will be contained in a slightly bigger set, which allows slightly better approximations. And the quality of the approximation is governed by the speed of growth of my sequence an. So what does this mean now? If my sequence grows at most like n log n, like the primes, then by Khinchin, the Lebesgue measure of this set is still equal to 0, and we contain the bad numbers. So property 3 still holds. We don't know about property 2. And if my sequence actually has positive density, then we have still the perfect characterization. So even 2 holds. So a full Kurzweil type result holds in this case. So let's not go into details what these technical assumptions and the multiplicatively defined sequence here mean. Let's just look on 3 examples that are covered by this theorem. First one is the prime rotation. Primes are very much multiplicatively defined. So let's look at the prime rotation. If alpha is badly approximable, we have this nice 0-1 law. We just need psi of p being a monotonic function, then sum of psi of p being divergent is equivalent to having infinitely many approximations. On the other hand, if my number alpha is a little bit better approximable, so if you can save a factor log n here, which is still by Kinch-Lebesgue full set. Then there is a counterexample. Then there is a monotonic psi such that the Lebesgue measure is 0, although the sum of psi of p diverges. So as I said, it's work in progress, but there is a special case that I had proven earlier in joint work with Emanuel Kowalski, which is already on the archive. The special case here was psi of p being 1 over p. This already contains quite some ideas of how to prove it. But of course, since it's just a function psi of p is 1 over p, I have some form of extra divergence, and I have a really nice function psi here. So it's a little bit more technical what is going on later on, but there is already something on archive if you want to check it. So this is the first example. Second example is, we don't talk about primes, but we talk about sum of two squares. This is also a multiplicatively defined sequence. We essentially have the same result. So if alpha is badly approximable, we have the same dichotomy. And if alpha is a little bit better approximable, in this case, we only have a square root log n by the density of the sum of two squares, then there is again a counterexample. So this is the second example. And the third example is now an example with positive density. So let's talk about the square-free numbers. If we now want to approximate with square-free numbers, we again, for badly approximable numbers, have the Kinchian type behavior. But if alpha is not a badly approximable number, we have a counterexample. So we can really recover the full Kurzweil type result by just approximating with square-free numbers. So this is one fact that comes into play here, is that the sequence of square-free numbers has positive density. So this is really important here. So we have also a lot of other sequences that have this property, but these are like three main examples of such sequences. Okay. So these things looked a little bit different, right? So I will still try to give you a joint proof of what's going on in the first part and what's going on in the second part, and to see how the multiplicative structure comes in, how the twin prime conjecture comes in, and where the diophantine approximation actually comes in. Okay, so let's speak first about the twisted diophantine approximation case. So again, twisted diophantine approximation is a limb subset. And the limb subset in this case is just, you look at a and alpha minus psi of n plus psi of n. There's a typo, this should be a and alpha plus psi of n here. So it's an interval of size 2 times psi of n. So how do we usually prove full measure? We look at the second moment. So if we just applied Jung-Erdős, we would like to have that the second moment is bounded from above by the sum of the measures. This is not going to work here for some reasons I will explain later on. So I will use a recent result with Victor Beresnevich and Sancho Villani, where we can find full measure of the limb subset if we allow to lose a constant times sum of measures, under the assumption that my sequence is still uniformly distributed in the unit interval. So if my intervals uniformly distribute, then I can get away with losing a constant here and still get full measure in the limb subset. So this is something I will use here. Okay, so in any case, we have to compute overlaps of these intervals. So let's just compute one overlap. Let's say n is smaller than m. Look at the Lebesgue measure of this. And this is, since it's just intervals, essentially this is equal to the measure of the smaller one times the indicator that the centers are close to each other. And now let's plug in psi of n as r over n. And we compute this. We say this is approximately the same. And then we get that we are just counting the pairs n and m, such that a n alpha is minus am alpha is smaller than r over n. This looks quite familiar with what we did in the first chapter. So this is just a pair correlation function. So in the end, this is essentially the same problem. We have to bound it, or we have to find an asymptotics of this. So this is the connection here. So let's just continue in computing a term here. So let's trivially rewrite the number of pairs where this is small can be rewritten as the sum of all h, such that h alpha is smaller than r over n, times the number of representations of h as the difference of an minus an. This is essentially an equality. So now the philosophy is the following. If my sequence is multiplicatively defined, then I should also see this in this function of representations here. So what I mean by this is that the number of representations should be asymptotically equal to some function f of n, which captures the density of my sequence, times some function g of h, which captures the arithmetic information. So g of h should be, in best case, a multiplicative function. And indeed, for the prime numbers, there is a conjecture that says, okay, we have this multiplicative information, and we should expect to have such a formula. So the Hardy-Littlewood conjecture says for every h, we expect this asymptotic formula. So we should expect n over log n squared, which is just coming from the prime density, times h over Euler phi of h times indicator h is even. So this h over phi of h and this h even just comes in by the fact that we only have odd primes. So all my differences, besides 2 of course, but all of my differences should be even. We only have one prime that is divisible by 3. So this also screws over the equidistribution in the other cases. So that's where the h of phi of h comes in. So it's not uniformly the same. We have some fluctuation, but this is what the conjecture says. But if we plug in now h is equal to 2, we would immediately get a twin prime conjecture. So clearly this is a very, very tough conjecture. It's out of reach with current methods. So we can't use it. However, people cared about this, so we can use partial results of this. So first result is that this conjecture has an upper bound that just differs by a constant. So there are at most 100 times more twin primes than we expect there to be. This is what an upper bound SIF gives us immediately. So we can use this one. We might lose a constant, but we can win back the constant later on. And if we don't care about primes, but we replace primes by rough numbers with this roughness parameter going to 0, then we actually get the correct asymptotic. Then we get the Hardy-Littlewood conjecture on these rough numbers. So these are the two tools from SIF theory that now come into the proof. So for the pair correlation, we needed the asymptotic. And for the twisted approximation, we were fine with losing a constant. So that's why in the pair correlation case, I need these rough numbers with this roughness parameter to get the asymptotic. And in the twisted approximation case, I can do it with primes because there are at most 100 times more twin primes than I expect there to be. There is a small technicality. I told you we need this equidistribution of the sequence A and alpha to apply our Borel-Cantelli result. But this is fine because Vinogradov showed almost 90 years ago that the prime rotation is uniformly distributed for all irrational alpha, actually. So we are fine in losing a constant. So we're almost done. We're almost done, but there is one catch. We still have this function g of h, which is this multiplicative function, and we have to average away this fluctuation. And the average here is going over the small Bohr set here. So it just captures all h, where h alpha is smaller than s over n. This is just log n many elements, and we have to average this multiplicative function away. So we want to get the number of elements in my Bohr set times the average value of my multiplicative function, which is quite easy to compute. So this is still something to do, and this is actually the main part of my proof. I will just give you some details, some ideas of the details I'm using there. So in order to understand the average of my multiplicative function on a set, it suffices to understand how many elements of my set fall into arithmetic progressions. So I only need to understand how many elements H in my Bohr set are congruent A mod D, where D is a constant or maybe slowly growing in n. So maybe growing like log n. So my approach of doing this, there might be other approaches for this. My approach was the following. If I know that my H is in my Bohr set, I can write H as Ostrowski expansion with respect to alpha. I get a lot of zeros in my Ostrowski digits, but I also get a bunch of non-zeros. So in this case, I get roughly log k many non-zeros, and k is about log n. So I get log n many non-zero digits here, which is enough for me because I just need unboundedly many. So the philosophy is that the Ostrowski digits should sort of give me some equidistribution. And if they were independent, then they would do that. But they are not independent because we have this Markov chain condition coming in the Ostrowski digits. So we have to include a Markov chain condition, and then we do a random walk on set D. And this is still enough. Markov chain condition is something that we understand quite well. A random walk on set D is also quite well understood. So in the end, I will do a Markov chain convergence theorem that provides me the equidistribution mod D. And if I have this equidistribution, I can go back, I can understand in arithmetic progressions my Bohr set, and this allows me to average away this function g of h, and the proof follows from there. Okay, so this is the proof for badly approximable numbers. So where do we actually use that these numbers are badly approximable? There is one. It's not really about averaging this function h over phi of h on this set. I use it there, but this is not the point why it fails for non-badly approximable numbers. The point is just that our Bohr set itself is too big. So let's say alpha is slightly better approximable with quality more than 1 over n squared log n. Then I will find stages n where my Bohr set is bigger than it should be. Bohr set is bigger than m log n for arbitrary m. And I would like to have the asymptotic c log n being equal to averaging this function over the Bohr set. And the function is just bigger than 1. So I just plug in bigger than 1. My Bohr set is too big, so I can't get this Poissonian correlation property here. So this is essentially also what happens in Walker's proof of that metrically we don't have pair correlation for the primes. This is just that the Bohr set is too big. This, of course, just applies now for Poissonian pair correlation. For twisted diophantine approximation, we just know we can't use second moment. But indeed, this is also sharp by using the idea of Kurzweil himself. In his paper, he constructs for numbers that are not badly approximable a malicious function psi that sort of always has big numbers just after the good approximation. And in this way, you can cook up a counterexample. So I'm just following here the ideas of Kurzweil, and you can still get the same result here. Okay. I have one more slide for you. Of course, every talk has to stop with some open questions. What about the gaps of the prime rotation? So we know it's false for almost every alpha, but I conjecture actually that it should be true for badly approximable numbers. So if alpha is a badly approximable number, then the prime rotation should have all correlation orders and consequently also the Poissonian gaps. So if we assume a uniform version of this Hardy-Littlewood k-tuple conjecture, which goes way beyond the twin prime conjecture, then this is true. So this is one indication of why the conjecture should be true. But of course, the question is, can we remove this hypothesis somehow? I don't think that we will live to the point where we can prove the full Hardy-Littlewood k-tuple conjecture, but maybe it's a chance of averaging away something that we can still show prime rotation has Poissonian gaps. I think this is a very, very hard problem, but I will still be interested to see some progress in this question. So this is about the first part, and the second part is about the twisted approximation for other subsequences. So we have this Kurzweil type result for certain sequences, as I mentioned before, the square freeze. But these sequences I always have positive density. So the question I have, is there a sequence AM that has zero density, but we still have this nice characterization of Kurzweil that the badly approximable numbers are exactly those that are approximated with this Kinchen type behavior? Okay, so these are my two open problems. If any one of you has any idea of solving this, I would be very much interested in getting your input. And I will stop here with my talk. And thank you all for your attention.
Okay, well, let's thank Manuel by some kind of round of applause. Virtual is fine, real also. Okay, and we still have time to maybe ask questions a little bit. Anybody wants to comment? So can you show the previous slide
Yes.
one more time? So there are many results throughout the talk. So let me just try to understand. You said that so the conjecture is that for badly approximal alpha and for primes you have Poissonian gaps, and you said that it's known for almost all alpha.
No, it's wrong for almost all.
Or it's wrong for almost
It's
all.
wrong. It's wrong. Yes, it's wrong
Right,
for almost
right.
all.
Okay, that's just the first. But it is true for there are no examples of alphas for which it's true.
No, there are no examples. Yes,
Mm-hmm.
we don't even know the existence of one. So
Right,
it's not
that's what
even
I'm
no
saying.
explicit one, but we don't even know the existence of any such
Mm-hmm.
alpha.
Okay.
So I think the alpha has to be, if there is one, the alpha has to be essentially badly approximal. Maybe you can get away with something a little bit more approximal, but not much more.
Mm-hmm. I see. Okay. Other questions? No, there are no other questions. Okay, let me ask one more thing. So in the themes around Kurzweil's theorem, so basically, if alpha is badly okay, so fix a function psi from your set M, or how it was called, and then no, let's not do this. Let's fix alpha. So we're twisted approximation, so we're fixing alpha. And Kurzweil says that if alpha is badly approximable, then this set of functions psi is divided into M and the complement of M.
Yes.
And M gives full measure, and not M gives zero measure.
Exactly. Yes.
Okay, and also, so now take alpha, which is not badly approximable. Then the set of all functions psi also divides into two
Yes.
parts. We can call it
Yes.
M alpha and M alpha complement, right? And there is a very nice paper which gives a characterization of this
Yes. Yes. The paper of Fuchs and Kim, you mean?
Fuchs and Kim.
Yeah.
So yeah, I like this paper very much,
Yes.
and I always keep asking about it. What if you add this additional twist of having a subsequence? Can you do something?
Mm, I can do
I don't
something,
know.
yes.
It's not
Yes.
a, sorry, it's not a precise question.
I can do something. I don't think that I can do such a nice characterization as in Fuchs and Kim, but I can do something. Yes.
What about primes? What can you say about primes?
Yeah, so you will not get a precise formula. So if I go back to my results, let's say with the primes, I don't really have an understanding what happens if my alpha is between badly approximable and approximable by 1 over n squared log n.
Mm-hmm.
So it's I expect neither of the bounds to be sharp.
Mm-hmm. Oh, I see. So that's
So in this statement here, I expect neither of the bounds to be sharp unless my set bad fa is actually just bad, which is in the positive density case. And the second inclusion here is essentially trivial if one follows what Kurzweil does. And I think in this part one can probably also essentially follow what Fuchs and Kim do, but it's not really giving a lot of information then.
Mm-hmm. Okay, thank you. That's very interesting. Other questions? I don't want to spend the question period by myself. So maybe if there are no other takers, let's thank the speaker again. This was very nice. Thanks for volunteering to give a talk, and thanks for telling us about these wonderful results.